The transition to the integral case. The following technique lemma allows for an elegant transition by using randomization. Definition 12.13. Algorithm A verifies a C integrality gap for the linear program CAP if it receives as input real numbers WIS and outputs an integral point X wave which is feasible for CAP, and C times the summations of WIS times XIS wave summing for all index pair IS is greater than or equals to the maximum among all the summations of WIS times XIS summing for all index pair IS, and the maxima is taken among all feasible X's. Lemma 12.14. The composition lemma. Suppose that A verifies a C integrality gap for CAP in polynomial time, and X is any feasible point of CAP. Then one can decompose X over C to a convex combination of integral feasible points. Furthermore, this can be done in polynomial time. Let the set X to the L such that L is in I be all integral allocations. The proof will be the set lambda L such that L is in I such that 1 for all L in I, lambda L is greater than or equals to 0. 2. The summations of lambda L summing for all L in I is equals to 1. And 3. The summations of lambda L times X to the L summing for all L in I is equals to X over C. We will also need to provide the integrality gap verifier. But first, we show how to use all this to move back to the integral case while maintaining truthfulness. Definition 12.15. The decomposition-based mechanism. 1. Compute an optimal fractional solution X star and the VCG prices pi to the f of v to obtain a decomposition X star over C equals to the summations of lambda L times X to the L summing for all L in I. 3. With probability lambda L. 1. Choose allocation X to the L. 2. Set prices pi to the R of V equals to Vi of X to the L over Vi of X star times pi to the f of V. The strategic properties of this mechanism hold whenever the expected price equals the fractional price over C. The specific prices chosen satisfy, in addition to that, strong individual rationality, i.e., truth-telling ensures a non-negative utility, regardless of the randomized choice. VCG is individually rational, hence pi to the f of V is less than or equals to Vi of X star, thus pi to the R of V is less than or equals to Vi of X to the L for any L in I. Lemma 12.16. The decomposition-based mechanism is truthful in expectation and obtains a C approximation to the social welfare. Proof. The expected social welfare for the mechanism is 1 over C times the summations of Vi of X star summing for all index I, and since X star is the optimal fractional allocation, the approximation guarantee follows. For truthfulness, we first need that the expected price of a player equals her fractional price over C, i.e. the expectations of pi to the R of V taken among lambda L is equals to pi to the f of V over C. So the expectation of pi to the R of V taking among all the set lambda L such that L is in I is equals to the summations of lambda L times Vi of X to the L over Vi of X star times pi to the f of V summing for all L in I, which is equals to pi to the f of v over vi of x star times the summations of lambda L times vi of x to the L, summing for all L in I, which is equals to pi to the f of v over vi of x star times vi of x star over c, which is equals to pi to the f of v over c. Fix any vi in capital V minus I. Fix any v minus I equals to is in capital V minus I. Suppose that when I declares vi, little vi, the fractional optimum is x star, and when she declares vi prime, the fractional optimum is z star. The VCG fractional prices are truthful, hence pi of x star minus pi to the f of vi v minus I is greater than or equals to vi of z star minus pi to the f of vi prime v minus I. By 12.6 and by the decomposition, dividing 12.7 by c yields the summations of lambda L times vi of x star to the L, summing for all L in I, minus the expectations of pi to the r of vi v minus I, where the expectation is taken among lambda L, which is greater than or equals to the summations of lambda L times vi of z to the star to the L, summing for all L in I, minus the expectations of pi to the r of vi prime v minus I, where the expectation is taken among lambda L. The left-hand side is the expected utility for declaring vi, and the right-hand side is the expected utility for declaring vi prime, and the lemma follows. The above analysis is for one-shot mechanisms, where a player declares his valuation up front. The bidding languages model. For the query access model, where players are being queried iteratively, the above analysis leads to the weaker solution concept of ex post Nash. If all other players are truthful, player I will maximize his expected utility by being truthful. For example, consider the following single item auction for two players. Player 1 bids first, player 2 observes one's bid and then bids. The highest bidder wins and pays the second highest value. Here, truthfulness fails to be a dominant strategy. Suppose 2 chooses the strategy: if I bid above 5, I bid 20, otherwise I bid 2. If one's true value is 6, his best response is to declare 5. However, truthfulness is an ex post Nash equilibrium. If 2 fixes any value and bids that, then regardless of 2's bid, one's best response is the truth. In our case, if all others answer queries truthfully, the analysis carries through as is, and so truth-telling maximizes I's the expected utility. The decomposition-based mechanism thus has truthfulness in expectation as an ex post Nash equilibrium for the query access model. Putting it differently, even if a player was told beforehand the types of the other players, he would have no incentive to deviate from truth-telling.